In this video, I want to take a look at how to find a basis for a column space of a matrix. And really, I have three ways to do it. The first one is simply to take the transpose and do what we did in the last video for finding the basis of a row space, right? Because when you take the transpose of a matrix, all the columns turn into rows and vice versa. So just find the basis for the row space. And then, of course, transpose them back. In doing this, you will get a basis for the column space, but it won't be made up of columns that you already have. There'll be other vectors that span the same space. Okay. We could do column operations like we do row operations. The issue here is that number 3 here, using row operations, doesn't keep the column space the same. And so doing row operations when you're looking for a column space changes the column space. Okay. However, if you do column operations, just like you did row operations, we could get away with it. Now I'm going to focus here on number 3 here, using row operations. Because although I said it changes the column space, there's some interesting things, right? Notice here, I have this matrix here, and if I look at the column space, it's the span of the columns. Of course, one of the columns is 0, so it doesn't really contribute anything to the span. So this is just the line spanned by the vector 1, 1, right? So 1, 1, you got that line here. Now, if I were to do a row operation, and you can think of this row operation either 2 ways. Either I multiplied that top row by 2, or I added the bottom row onto the top row. Either way, I end up in the same place. And notice now the span of these two columns is the spanning the vector 2, 1. So I have my drawing wrong. Hang on a minute. There we go. Now we're spanning the vector 2, 1. Okay. It's still a one-dimensional space, right? It was a line to begin with, it's a line afterwards, but it's a different line. We have changed what the span is. So if I found, a basis for this span, it's not the same as the basis for that span. So looking for a basis for column space, doing row operations, you got to be a little careful. However, it turns out that doing row operations really is a cool thing because of the following theorem. Now this theorem is not in the book, but I will show how it proves the ones that are in the book. Anyway. So consider the following matrix here. It's a 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, one of my favorite matrices. One of the problems I've always had with this matrix, though, is that it is not invertible. The determinant is 0. What happens is there is a linear relationship among these columns, and namely column 3 is column 2 times column 2 minus column 1. Right? You can double check here. This 3 is 4 minus 1. The 6 is 10 minus 4. The 9 is 16 minus 7. The entries in the third column are the corresponding entries 2 times in the second column minus the ones in the first column. Right? Now, let's try a row operation on this. So let's swap 2 rows. What am I going to do? I'm going to swap the second and third rows. Notice, this linear relationship is still the same. That the third column is 2 times the second column minus the first column. Okay. Let's try another row operation. This time I'm going to multiply by a constant. What did I do? I multiplied the first row by 2. Right? So going from here to here, multiply the first row by 2. Is it still the case that the third column is 2 times the second minus the first? Well, the stuff down here didn't change. But now notice this 6 is 8 minus 2. Yeah, it is. Okay. So that didn't change the relationship between the columns. And likewise, if I add a multiple of one row to another, so let's see, the first row is the same, the second row is the same. So it looks like what I did is I added 2 times the first row to the third row. Okay. 2 times the first row to the third row. Is it still the case that the third column is 2 times the second one minus the first one? Well, the first two certainly work. Is that 15 equal to 24 minus 9? Yes, it is. Okay. So these row operations do not affect the relationship between the columns. They're definitely changing the columns and they're changing the column space, but they're not changing the dependencies among the linear dependencies among the columns. Okay? Now, this is by no means a proof of the theorem I stated, but it could indicate how you might go about doing a proof. You'd have to write a general matrix with the A11, A12, right, and then try each of these things and see what it does to the relationship between the columns. And the answer is it doesn't affect the relationship at all. Now, the theorems that are in the book that are related here is that says if you have two matrices, A and B, that are row equivalent, right, that you can get from one to the other by a sequence of row operations, then a given set of columns in A are linearly independent if and only if the corresponding set of columns in B are linearly independent. This is a consequence of the thing that I set up here because the linear relationship stays the same. So if they were independent, doing row operations keeps them independent. If they are dependent, then they will still be dependent, and they will be dependent in exactly the same way that they were before. Right? So I'm saying a little more with my theorem than what the book has here. And likewise, they have a given set of columns of A form a basis for the column space of A, if and only if the corresponding set of columns in B form a basis for the column space of B. Okay. Now, remember, the column space is the span of those columns, of all the columns. And if all of them are not a basis, it means they must be linearly dependent in some way. Well, if they're linearly dependent in some way, then doing the row operations doesn't change the dependency. So the ones that you can throw away, because they're linear combinations of the others, would be the same in each of the two matrices. And so, once you throw away all the ones that are dependent on the others, you work yourself down to an independent set of columns for one, and it's the same set as the other, because all the dependencies are the same, exactly the same. Okay. So here's an example. This is the same matrix that I used in the last video, except for one thing. That is, in the last video, I actually had a typo. That is, I had this second row as 16118 instead of 16168. And I said the reduced or echelon form of it is this thing, which with the way I had it typed in the last video, it isn't, because with a 1 there you don't get this. But with a 6 there, you do. Okay? So sorry about that. I don't know if anybody noticed that, but in the last video there should have been a 6 right here. So let's take a look at the dependencies. Let's take a look at this column space here and see what columns are dependent and independent. Right? If I were to take this and put it in reduced or echelon form, this works for any two row equivalent matrices. However, if you get the reduced or echelon form, there's a lot of really nice things that you can see. Okay. For instance, when I'm looking at this thing, I can clearly see that column 2 is dependent on column 1 or vice versa, right? 1 is a scalar multiple of the other. Column 2 is definitely 2 times column 1. Right? Column 1 and column 3 correspond to those two leading ones in the reduced or echelon form. And those two are definitely independent. There is no way you're going to do a scalar multiple of column 1 to get column 3. But then, because it's in reduced or echelon form, it also makes it easy for me to see all the relationships. For instance, I can see very quickly that column 4 here is 2 times column 1. Sorry, it's 4 times column 1 plus 2 times column 3. Right? This 4 comes from multiplying that by a 4. This 2 comes from multiplying that by a 2. And the zeros, of course, multiply the zeros by anything and add them up. They're still going to be 0. So this column here, column 4 is 4 times column 1 plus 2 times column 3. Likewise, the 5 and the 3 tell me that column 5 is 5 times column 1 plus 3 times column 3. So there is the relationship between these columns, really easy to see when it's in reduced or echelon form. And we can go back and check. Do the same relationships work here? Is column 2 6 times column 1? Yes, it is. Is column 4 4 times column 1 plus 2 times column 2? So if I do 4 times this plus 2 times that, yes, that's 4. 4 times this plus 2 times that, yep, that's 6. 4 times this is 8 plus 2 is 10. 4, 12 plus 6 is 18. Sure enough, C4 is still 4 times C1 plus 2 times C3. And lastly here you can check for C5, column 5. should be 5 times the first column plus 3 times the third column. So 5 times this plus 0 times 3, yes. 5 plus 3 is 8, yes. 10 plus 3 is 13, yes. 15 plus 9 is 24. Okay. So when you're looking for a basis for the column space, the best way to do it is to just put the matrix in reduced or echelon form. The columns over here that have the leading ones are the basis for the column space of the reduced or echelon form. And it also means that the same two columns will be a basis for the column space of what you started with. So the basis for the column space for matrix A is column 1 and column 3 together, right? The other 3 columns are dependent on those two, and they're not needed in the basis. I want to finish this video with, well, a couple of things. 2 things left. Same matrix. In the previous video, we found a basis for the row space, but we found it in terms of a couple of vectors that weren't actually rows of the matrix itself. If you want to find the basis for the row space in terms of actual rows of the matrix, then the way to do it is to take the transpose and do what we just did here. So if I take the transpose of this matrix and put it in reduced row echelon form, I see this. The leading ones are in the first and second columns, which means the first and second columns of this matrix are linearly independent. The other 2 are dependent upon them. In fact, you can see that column 3 is just the sum of column 1 and column 2, and that column 4 is just 3 times column 2. And you can double check here that that's the case in the matrix that you started with. But what it says is that these 2 columns are a matrix for the column space of A transpose, which means that the first 2 rows are the basis for the column space. They're basis for the row space of A. So it's the same process. It's just that if you want to get rows, you've got to do the transpose first and then look at columns and then convert it back. Okay. Now, this actually is a problem that comes up from time to time, where you have a set of vectors that span a space, but you want to know which ones you need from that set to be a basis. Okay. So you got to throw away all the ones that are dependent. Well, the quickest way to do that is to just take those vectors, write them as columns of a matrix, put in a reduced row echelon form. The columns that have leading ones correspond to the ones that you want in your basis. The columns that don't have leading ones, they're linearly dependent on the others. And the linear dependence is easy to see because you got all these zeros here, and you can just see which ones add up to get these other columns. Okay. I'm not going to do an example of that. It's exactly the same as what we did up here.